So we're going to continue in section 11.2, curves, polygons, and symmetry. And we left off last time talking about different quadrilaterals. In particular, we stopped with square. Does that sound right? Good. So the last quadrilateral is actually a kite. A kite's a very interesting one because it doesn't sort of follow the pattern that we were establishing up to that point. We sort of took something really broad and got much more specific, but it all fit, was the same criteria until we got to square. A kite is a quadrilateral with two adjacent sides congruent and the other two adjacent sides also congruent. So what you see happening is that these two sides are equal, right? Hash marks, one hash mark. And the other two sides are also equal for it to be considered a kite. Interestingly enough, that second one, which you probably would look at it and say it looks like an arrow or maybe an arrowhead, is also a kite with this definition. These two sides are equal, and these two sides are also equal. And that fits the definition of a kite. Probably not one you're going to fly, right? Not the image you're thinking of, but it is a kite. So what we're going to do next is we're going to answer some true-false questions about shapes. And we're going to do them all together to try to move through them a little more quickly. And we'll see what you guys think. An equilateral triangle is isosceles. That is a true statement. Isosceles means it has two sides the same. Equilateral means it has three. So if you have three, then you've definitely satisfied the I have two criterion. A square is a regular quadrilateral. It's true. Quadrilateral, certainly it's that, right? It's got four sides. Regular means it has four equal angles and four equal sides. That's a square. So that one's true. A square is a rhombus with a right angle. That's true. Rhombus means it has four equal sides. Square does that. And does it have a right angle? A square has that too. So that is correct. All angles of a rectangle are right angles. That's true. And I don't think if you flip back that you'll see that that actually is exactly our definition. We sort of think about it that way all the time. But a rectangle's definition is actually a parallelogram with a right angle. But having one is actually enough to automatically get all four with the other condition about parallelogram on there. For very much the same reason that last question that you guys had, the one Avery mentioned on number 2 about the parallel lines and the perpendicular lines, because you are inside of a plane, and so it forces that to happen. But a rectangle is an isosceles trapezoid. What do you think? It's true. Do you notice a pattern? It is. If you have an isosceles trapezoid, it means that you have one or two pair of parallel sides. A rectangle has that, right? And isosceles means that the base sides are equal, and in a rectangle, they're equal as well, right? So yeah. Some isosceles trapezoids are kites. It's true. Specifically, squares. Squares are, in fact, isosceles trapezoids, much like a rectangle would be. And they have the two sides equal here and two sides equal here, or here and here, whatever you want to draw them as. The last one, if a kite has a right angle, then it must be a square. That is false. Somebody said it. After all the truths, I thought somebody would tell me it was true. Let me actually draw that one for you. If I use my corner of my grid here, over here, and I need them to be equal length, so we'll go to here and here. Okay, so those two, actually, I'll use this point. There is a right angle. Yeah? And I do have a kite, but it is not a square. So there is a way to draw that one that does not fit that description. Now, if you said the if then in the other order, it would work. If you have a square, then it is a kite. That's actually true. But just because it's a kite with the right angle does not necessarily make it a square. Okay, let's take a look at the organizational hierarchy of polygons. Is this in your actually typed already in your notes? No? Okay, so draw this in. I've alluded to some of these sort of relationships already. So far, we've only talked about two types of polygons. There's certainly more. But triangles and quadrilaterals. And you can't be a triangle and be a quadrilateral. You can't be a quadrilateral and be a triangle. So they're completely separate branches on the diagram. Okay, one has 3 sides, the other has 4. So if you're in the triangle side, if the triangle is scalene, it means it has 3 unequal sides. The other possibility is that it has at least 2 sides that are equal. That's an isosceles one. But you could have the additional consideration that all 3 sides are equal, and then you actually have an equilateral. So it's almost like you're starting out with something broad on top, polygons or triangles, and you go down and you get more specific. If you go over to quadrilaterals, it's far more interesting because there's more relationships going on. So with a quadrilateral, you actually can categorize a quadrilateral as either a kite or a trapezoid, the ones that this isn't all quadrilaterals, by the way. There are other possibilities, but the ones that we've talked about, okay? We have kites that are quadrilaterals, and we have trapezoids that are quadrilaterals. One type of kite is a rhombus, not the only type, but one is. It's a very specialized type of kite. A trapezoid could be an isosceles trapezoid, or it could be a parallelogram. And if it's both a parallelogram and a isosceles trapezoid, then it's a rectangle. And you see square here at the bottom because a square is something that actually fits all the criterion above. A square is a rectangle, a square is a parallelogram, a square is a kite, a square is a quadrilateral, and so forth. Squares are all these things that are above it. It's the most special, specific type of quadrilateral that we have. Okay, now at the very beginning of this lesson, the title of our section is actually Curves, Polygons, and Symmetry. We've now finished our discussion of polygons, which was the second piece, and symmetry is what's left. So the rest of what we're going to look at today is going to be symmetry. The first type of symmetry that we're going to talk about is called line symmetry. So line symmetries will have a line of symmetry. It is a line, which is its own image under a reflection in or fold along itself. The basic idea is it's a line that cuts it in half and the 2 sides are mirror images. So if you think about your person, like you personally, with the exception of the idiosyncrasies that make you you, and if you stood like this with the crazy face and everything, right, your line of symmetry would be the one that cuts straight through your nose, straight down the middle of your body, okay? That's your line of symmetry. So we can do this on some shapes, and other shapes we can't do this on. So I'm actually going to jump to the second shape because it's really easy to see it work on the second shape. One line of symmetry for our second shape would be right, I don't think I quite got it centered, but approximately there. So let me shift it over. It cuts the image in half, and if I folded it along the line, they would mirror, they would match right up. It's not the only line of symmetry. What else would be a line of symmetry here? A horizontal right through the middle, right? Again, I didn't draw mine well. I'll shift it so it will be better. More like that. So this one, the rectangle, has not only one line of symmetry, it actually has two lines of symmetry. And line of symmetry is often abbreviated as LOS, just so you know. Line of symmetry. So there's two. How about a square? Well, a square is a rectangle, so it has those same two that I already had, one here and one here, roughly speaking. Is that all it has? It has more. What else does it have? Yeah, its actual diagonals work. The diagonals of the other shape, the rectangle, they don't work. Because when you fold, actually, you take something that was a horizontal rectangle and turns into a vertical rectangle if you start trying to fold things along a diagonal line. But that works for a square because all four sides are the same. So what you actually end up with is, whoops, 4 lines of symmetry here. Over here on my first figure, what do you think about lines of symmetry? You could if it were a rhombus, but this one isn't. It's actually elongated, more like a rectangle is. So if I were to try to use the diagonal, it would turn it to make it look more like it's vertically long instead of horizontally long, so it wouldn't work. So this one doesn't have a line of symmetry. There's no line that I can draw where when I fold it, it matches up on itself. Okay, we have a bunch of shapes. And the question they ask is, how many lines of symmetry do the shapes have? So let's just go through them one at a time. The first one is what shape? What is that? It's a hexagon. Good. So you might see that you've got a line of symmetry right like there. Did anybody see that one? But if you have one there, it means you also have one here and here, right? Because it's the same, it's sort of a mirror portion of the diagram. Any others? Yeah, I'll change colors because they sort of change the way that they're being thought about. You have one right here. Yeah, every other middle of the sides would have one too. So this one has a lot of lines of symmetry. How many, in fact? 6. There are 6 lines of symmetry on this. How about our next shape, the shape that looks like an A? Does it have one? Yep, and just one is right. Again, I didn't draw it very vertically, but you can imagine that you did. And sure enough, there's just on this one, 1 line of symmetry. How about C? The oval shape. 2. There's one that cuts it in half sort of like this. Makes it look like a pill capsule or something. Maybe divide pills. The other one looks like this. So this shape has 2. How about the letter Z? Maybe seeing nods of no's. Yes, that's a 0. There are no lines of symmetry for that one. How about E? Just one. Where is it, Julie? Yeah, it goes from corner to corner, basically like that. That would fold up along itself, so we have 1 line of symmetry. It's the only one. How about F, that looks kind of like a fancy plus sign or arrows in all direction or whatever? There are 4. So you just should have the top to the bottom, or the top to bottom and left to right. And then you should also have the ones that look an awful lot like the last problem where it cuts it along those corners. And we end up with 4. Kind of fun, right? Lines of symmetry. The next type that we have is called turn symmetry. So turn symmetry takes an object and it rotates it a little or a lot, and where it rotates it by a specific amount, the image looks exactly like it did to begin with. So it's also called rotational symmetry because we're turning or rotating it. It says specifically a figure when turning it by some angle degrees less than 360, because if you turn something 360, it's back where it began, around a single point called the turn center, causes it to match up with the original figure. So there are three shapes here. Two of them are very familiar. We see them a lot. The recycle one and the wheel. And what we're looking at is we're looking at the type of rotational symmetry. So the first one, the recycle logo. The recycle logo has to turn like 1/3 of the way. If you're to take 360 and divide by 3, 1/3, you get 120 degrees. So it has a rotation of 120 degrees around its center. So we would say that it has a 120 degree turn symmetry. But it's interesting because if you turned it another 120, it would still do the same thing again. And if you did 120 twice, that's 240. So it has a turn symmetry of 120 and 240. Okay. We can do that with any shape that we wish. So if you take a look at that recycle symbol, the reason that it's 120 is because we did 360 divided by 3. There are three sort of images where I turn it 1/3 of the way and I get back to where I go. If you take a look at the car tire, how far do you believe you would have to turn it, or how many times or whatever your description is you'd want to, in order to get that image again? Can you tell? It's 6. There's sort of these 6 repeating images. You can almost think of it as these 6, they're kind of like triangles. They're not quite triangles, but around here, right? Those have to line up on themselves, and there's 6 of them. So as we look at our tire, to find the turn symmetry, we divide 360 by the number of similar shapes or possible rotations. 360 divided by 6 is 60. So I don't think I have a slide for my last one, but can you tell me what I would have to divide by on the third figure? 4. I have 4 similar shapes. So if I took 360 and I divided by 4, I'd get 90. And again, when you add it to itself, kind of like I did with that first shape, the recycle shape, 90 plus 90 would be 180. So there's a 180 symmetry or turn symmetry. And plus another 90 would be a 270 turn symmetry. They'd all be there too. Okay, we've got 3 shapes. And we're asked to find the amount of the turn for the rotational symmetry for the figures. And when it asks us that, it's asking us for the first rotation, right? It's not really wanting us to list them all out, although you can if you wish. It's enough to simply talk about it being the first one. So what do you think that you would have for the turn symmetry value on the first shape? What is it? 180. Yeah. There are 2 images that are the same. Sort of if you were to sort of piece them apart right here, you can see how it breaks it into 2 pieces that are images the same. And so we would have 360 divided by 2 for 180 degree rotational symmetry. That's Chevy, right? Yeah. Okay, what's the next one? You guys recognize that one? Is it Nissan? No? What is it? Chrysler? It's a car or something. I'll have to figure it out and tell you next time. right, what would I divide by for this one? 5. Yep, I would divide by 5 to get my rotational symmetry. So what is 360 divided by 5? It's the most unusual value we've had. Somebody have a calculator? Oh, Ashley's got it for us. So Elizabeth does. Okay, 72 is right, yeah. It's 72 degrees. So this has a 72-degree rotational symmetry. How about the last shape? What would I divide by? Yep, 6, which we've seen a shape like that already. And if I divide by 6, I get 60. Please note, a figure can have line symmetry, rotational symmetry, both symmetries, or neither symmetry. Okay, so those are independent things to describe them by. They don't have to have one or the other, both or neither. I mean, any of those are possibilities. The last symmetry we're going to talk about. So here's what we're going to do. I'm going to talk about the last symmetry. I'm going to encourage you to go start the homework with the Success Center. We will do group work on Friday or on Wednesday, but the homework will not be due till Friday. The reason I'm encouraging you, even though the homework's not due till Friday, to get it started earlier is because right now, as far as we know, there are no Success Center times on Wednesday or Thursday night. So starting it now would be in your best interest for support if you need it. Okay, there's one more type of symmetry, and that type of symmetry is called point symmetry. So we've got line symmetry, turn symmetry, and now this is point symmetry. Point symmetry is specifically a figure that has 180-degree rotational symmetry about the turn center. So point symmetry is really just a specialized case of turn symmetry, right? It's turn symmetry that's 180 degrees. The turn center becomes the midpoint of a line segment through any point and its image. So all of these have point symmetry. Can you imagine on each one of them rotating them 180 degrees? And can you see that for sure when you do that, think about a spinner on a board, rotated 180 degrees, that it will land right back on top of itself. And you can imagine, hopefully in all the cases, there's 6 of them there, where the turn center is, right? We didn't really talk about that significantly on the last one, but the turn center is the point we're rotating around. So hopefully you're seeing that image as well. All right, symmetries of a circle. Circles are amazing, like the most convenient, beautiful shape ever. A circle has infinitely many lines of symmetry, each of which passes through the center of the circle. What is another name that you know for that shape? A diameter. Every diameter, and there are infinitely many, is a line of symmetry. There's a few of them drawn. Not great, but you can get the idea. All of the circle's lines of symmetry intersect at the circle center. That should make sense. They're all diameters, right? Yeah. A circle also has infinitely many turn symmetries, right? No matter what degree you turn it by, its image is already there, right? And since there's infinitely many values between 0 and 360, there's infinitely many turn symmetries as well. And the circle has point symmetry because it has a 180-degree turn symmetry. Circles are wonderful. Or maybe they're awful for all of those same reasons, depending on what you're doing. I don't know. Okay, so again, we will not turn in the homework on Tuesday or on Wednesday. We will do the group work at the end of class. We'll move on to 11.3. But this assignment will be due on Friday, and you should start it now, but not the group work part, if you would like to, so that you can get support from the Success Center or have more times to come see me if you'd like as well. Have a great couple days, guys.